So today we are going to start with the next topic, that is the part of the basically the greedy algorithms only. So we use greedy algorithms for the different kinds of applications that we come across in the real life, right? So one of the applications is your text compression. See, in the real life, like we people are using the computers for the decades, right? So since the you can say the invention of the computers and its usage, we know. So the most bottleneck that we came across, it is the memory, right? So whether it was in the 1990s or 1980s, we say, or we say in the current scenario, every time we are having a shortage of the memory, because these are the things where, like when we are processing something, when we have to do the storage. So in that case, these are the things we come across, and we have to take care of that because these are a costly affair. So whether we were working in the 1990s, or we see when in the current scenario when we talk of big data, still we are shortage of the memory. So although we have you can say the hard disks where we can store terabytes of data, petabytes of data, right? So we have a storage space, but still the size of the data we always have is beyond that. So we are always looking for the solutions to such kind of problems, that we are able to save the memory. So one you can say one solution to saving the memory is to compress the data that we are storing. So different kinds of compression techniques have been developed over the decades in order to save the memory. So it's not only about saving the memory. When once we have compressed the data, size, if the size of the data that we are using is reduced, it is you can say we are able to send it faster also. So we are able to reduce the time, and we are able to send data for communication using the lower amount of bandwidth also. So it's not just the memory because of which we are looking forward to such kind of solutions. It's because that when we are communicating with someone and we have to send large file, you people may have experienced, like when we are working with large amount of data in the Java programs, when you write, sometimes if you have faced the problem of uh, uh, size of the memory heap is small, you can say such kind of problem we come across. So that means the your size of the memory, or you can say the heap size is less. So for you have one option to increase the size of the heap in the Java when you're working with any of the IDE or JDK toolkit. But again, there also there is a limit to how much we can increase the size of the memory. So we are always having some limitation to that, and we cannot work beyond that. Like in your minor projects, you will be working on large kind of number of applications, and there you will say, so it is the only size of the data that can be supported by laptop, because sometimes your project may be require large number of computations where you have a problem that your RAM size is small. So it may be like for the big data applications, like when you have to work with a Hadoop or some other softwares, you maybe require the you can say the processor or to be the 8 GB or 16 GB. And along with that, if you try to load the large amount of data, it may be your RAM is not supporting or your hard disk is not supporting. So we always have some kind of limitations. So in order to handle such kind of limitations, these data compression techniques are there. And like the data, there are some specialized techniques. There are certain you can see the common techniques which can be applied, right? So you can say like if you for the audio, or you can say for the multimedia data, like the JPEG, MP3, MP4, all these are the data compression techniques which are used to store the multimedia data. And these are specialized techniques only, and they cannot be applied to the text for compressing the text. And again, and you can say it, so because they are specialized for multimedia data, these techniques cannot be applied for compressing the text. Then another way we are compressing the text, like we we are asking you that you can zip your file, you can create a RAR file. Then you have so many techniques, you and programs in the Linux also in order to compress the data, right? So besides these techniques, there are certain algorithms which, see, when we are using, we are compressing the zip file, or you can say that we are creating a RAR file. They have their own mechanism there of compressing the data. So all these techniques are again categorized as the lossy compression techniques and the lossless compression techniques. That means there are certain techniques which store the data but in the form of a summary. So so this is called as a lossy compression technique, right? So when the data is stored, you can say in the form of a summary, so you cannot get back the original data, right? So your JPEG and MP3, MP4, they are basically the lossy compression techniques, because when they are storing this multimedia data, and let's say it is a video with lots of certain pixels in between, you may not come across, you may not be able to identify. But when if we have to do the compression of the text, loss of few characters in the text or loss of few words in the sentence may altogether spoil the whole text, and the text may become useless. So in that case, we cannot apply the lossy compression techniques for the compression of the text. We need to have the lossless compression techniques for compressing the text. So the two lossless compression techniques which we are going to study for the text compression, they are the Shannon Fano encoding and the Huffman coding techniques. So in the see, when you all know that how the data is stored in the machine. So it is all the characters, they are represented using the ASCII codes, and these ASCII codes basically the ultimately representing the bits and the bytes, right? So every character is represented using certain number of bits, and the conversion is done in the form of ASCII codes. And this is basically called as, you can say, one kind of encoding technique that is called as fixed encoding techniques. But in the real life, see, you can say this fixed kind of encoding techniques where ASCII codes are being used. So the drawback of this kind of technique is that it is not taking care of any such information. Like when we are storing some text, we know there are certain characters which are used repeatedly, whose frequency is very high as compared to the other characters. So in that case, we can devise some mechanism where the frequency, you can say the characters which are having high frequency and the characters which are having the low frequency, so they can we do something with this particular information and find out a mechanism, or you can say the compression technique, with the help of which we are able to reduce the memory. So reducing the memory is reducing the amount of space taken by the text is the main goal behind the text compression technique. So we are going to study about these techniques, and we will see how using the Huffman coding we are able to save the memory, and how you can say the methodology or the mechanism which is being followed by in the Shannon Fano coding for in order to save the memory. So let's move on to the first technique, that is Huffman coding. So it was given in 1950s, and it is a lossless data compression technique, as I have told you. So lossless compression, because if see, when we are encoding, let's say you are creating a zip file, right? And in the zip file you are sending me some assignment. And when I receive that, see, this is kind of encoding you have done. You have compressed the data in form of zip file. And when I'm getting that zip file, and I'm going to decode that. If during the decoding process, I'm not able to get the data in the original form, I won't be able to assign you any marks for that particular work, because it will be showing me some kind of garbage which I'm not able to understand. So therefore, in the text compression, we need to perform the lossless data compression technique, so that the way you have compressed the data, I should be able to get that particular data in the same form. So in that case, when you are encoding the technique you have used, so you need to send me the decoding technique also. That means from the zip we already know. So I have to, you are going to zip it and I'm going to unzip that because they are the built-in softwares. So similarly, if you have designed your own technique, you have to tell me the decoding technique also for that you have followed for the compression of data. So in the Huffman coding, we say the idea is to assign variable length codes. I've told you, so when we are assigning the variable length codes, we are able to save a lot of memory that we will see with the help of this an example. So lengths of the assigned codes, basically they are based on the frequencies of the corresponding characters. As I've told you just now, that in the text, when the text is written, you can easily make out that in most of the text you can see there are certain characters which are used whose frequency is very high and the others is very low. So we are going to take up this particular kind of information, you can say this knowledge, in order to compress the text. So the most frequent character gets the smallest code and the least frequent character gets the largest code. Here you can see where the characters which are having high frequency, they get the smallest code, and the characters which have the low frequency, they will be getting the largest code. So the variable basically these codes, they are assigned the prefix codes, means the codes are assigned in such a way that the code assigned to one character is not a prefix of the code assigned to another character. So why we are using this particular technique, why we are focusing on assigning the unique prefix code, because if the two characters have same prefix code, in that case, while performing the decoding process, there will be ambiguity. So the decoding process may not be correct as it was done in the encoding. So in order to get rid of this particular ambiguity in the decoding process, the unique prefix codes are being used. So let you see, let A, B, C are given codes 0, 0, 0, 1 and 0. So now in this particular case, all these codes, they are having the prefix 0. So in that case, let us say C is having 0. So if you are given certain code like this, if this is the code, so here is an ambiguity whether the person who is receiving this code, he should interpret CAB or he should interpret CC. Sorry, yes, it is C, then again C, and it may be the B. See, either it is CCB or it is CAB. So how it should be decoded? So that means there lies an ambiguity when we are using the same prefix code. So in order to get rid of this particular problem, the unique prefix codes are being assigned when we are performing using this Huffman coding technique. So what is the actual way of compressing the data using the Huffman coding? So the first step is to build a Huffman tree from the input characters, and second technique is traverse the, you can say the second step is to traverse the Huffman tree and assign codes to the characters. So you can say, so while building the Huffman tree, we are encoding, and in the second step, we are decoding that particular tree. So that means when we are doing certain kind of compression, we are encoding. Here you can say you can say this may be considered as the drawback, or you can say this is the limitation, or this is the requirement of the Huffman coding, that whatever Huffman coding procedure you have followed, you have to send that particular table, or you can say the mechanism to decode that particular technique to the receiver also, right? So the various steps involved in the Huffman tree are like, first of all, you have to create a leaf node for each unique character and build a min heap of all the leaf nodes. So here we are going to use a priority queues, where we priority queues, and then while the implementation, you will see you have to use this min heap operation you will be performing. So why we are doing that? Because in this particular technique, we are going to extract the two nodes with the minimum frequency from the min heap. That means we are going to sort the complete data. So first of all, we are going to sort the complete data, and after sorting, we will be extracting the two nodes with a minimum frequency. Then we create a new internal node with frequency equal to the sum of the two node frequencies, and we make the first extracted node as the left child and the second extracted node as the right child. And this node will be added to the meaning, and we will keep on repeating through this step until we are able to reach to the root node of the tree and the tree is complete. So let's see this example. So we have the characters A, B, C, D, E, F. Let us say we are given certain text, and from that particular text we identified that this text contains only 6 characters, and and for each character we have a frequency assigned to each of them. We have identified that from certain text. So you can say that task has been done for you. And it may be that you may be given some text. Let us say you are given one sentence of encode. Let's say the one sentence that you are given is encoding example. From the encoding example, you can see E is having the frequency of 3, N is having frequency of 2, C is having the frequency of 1, O is having the frequency of 1. So this is how you are going to convert that into the table. So from this table, what do? We see that the algorithm says create a leaf node for each unique character and build a min heap of all the leaf nodes. So how do we create the min heap? So what we are considering, you look at this example, we will start from the bottom. So here you see we have the character A and we are given the frequency of 5, and we have character B and we have the frequency of 9. And these are the minimum frequencies we are creating the min heap from here. So you can say, what do? We combine these nodes to create another node that is a parent node. So the 5 becomes the left child and the 9 becomes the right child. So and we in the node top node, what do? In the parent node, we are taking the sum total of the frequencies of both. So it becomes the 14. So 14 becomes, if we see this thing now, so now what we have the 4 more nodes, that is 12, 13, 16 and 45. From this 12, 13, 16 and 45, so the 14 will become the 12, 13, 14, 16 and 45. So what do? The next what we are going to do is we are going to merge the C and D, because they are having the minimum frequencies as compared to 14. So we say from 12, 13 and 14 we are going to merge the 12 and 13. So 12 and 13, when we merge, it gives a total of 25. So 25 will again we will add this node to the main heap, and now the order will become 14, 16, 25 and 45. So from this 14, 16, 25 and 45, we are going to merge the 14 and 16. When we merge the 14 and 16, we get 30. So in the again this 16, then we are able to get the new nodes. So for 30, then we have 25, 30, 50, 30, then 45. So from 25, 30 and 45, we are going to merge the minimum ones. So the minimum ones are 25 and 30, that combines together to form the 55. And finally, we are left with 55 and 45, that gives us 100. So here you can see at every stage what we are doing is we are looking at the one which is on the left hand side, it will be given as a 0, and the one on the right hand side, it will be given as 1. So on the basis of that, what we are going to see is how we are going to decode this particular tree. So here you can say the left node, the 45 is 0, right? So here you can see on the, if we start from the 100, the final parent node, that is on the root node. So here every branch I'm going to say, so from the 100, the left hand side f it is 0, and from the 100 we say on the right hand side, which is 55, it is 1. From the 55 we say from 55 to 25 it will be 0, and from 25 to C it will be 0, from 25 to D it will be 1, and then from 55 to 30 it is going to be 1. Then because we are assigning the values of zeros to the left child and we are assigning the values of 1 to the right child. So this is how at every path we are going to assign the values, and on the basis of that you can see, if we see it was 0, so the code for F is 0, and as we move from 100 to 55 to 25 to C, so it is 1, 0, 0. So here you can see the code for C, that is equal to 100, 1, 0, 0. Now let's see the code for D. It is 1, 0, 1. So here you can see the code for 1, 0, 1. So this is how we create the variable length codes using the Huffman coding in this particular example. So this is the technique for encoding. Right now, here you can say, since we have assigned these particular codes, and when we are setting that, we are going to send the, let us say the text was A B C D E F only. So what do? We combine all these codes and send only this particular code. Now how the user is going to, when we are sending this to the receiver, how the receiver is going to encode that. For encoding this, you need to send this particular tree along with your code to the receiver. So here you can see, if we see the time complexity of this particular algorithm, n is the number of unique characters, which is equal to, let us say, 6 over here. If there are n nodes and extract min is called, we know it requires 2 into n minus, it is executed 2 into n minus 1 times. So extract min takes O log n time as it calls min heapify. So the overall complexity of this particular technique of Huffman encoding is O n log of n. So here you can see we have to apply the min heap operations. We are extracting the min heap, extract left, extract y, and we are doing the insertion process over here. Fz is equal to fx plus fy. So here you can see fx plus fx is the left node and fy is the right node. So this is how we keep on operating. So we can see over here there are n iterations of the loop, n is the number of characters. So each loop iteration may take O(n) time if not implemented properly. And using the binary min heap, we find the minimal element, deleting insertion and insertion then takes O log n time. So the total time taken over here is being the n log of n time. Then how to perform the decoding? As I told you, in this particular technique, what is supposed to be done is we need to have the decoding technique also. So when we are given the binary string, decode the encoded data using the Huffman tree. So we require that. So we start from the root, do the following until a leaf is found. If current bit is 0, move to the left node of the tree. If the bit is 1, then move to the right node of the tree. If during traversal we encounter a leaf node, print that character of the particular leaf node, and then again continue the iteration of the encoded data string from step 1. So here you can say, let us say you are given this particular, can you decode for the same example 0, 1, 1, 0, 0, 1, 0, 1. So you can try out what will be the characters you will be getting from this particular code that we have generated using the Huffman decoding technique. Then another lossless data compression technique that was given by Shannon Fano. Shannon Fano. So here again we are see, in this particular technique also different techniques have been devised with the main with the single objective of reducing the amount of memory required for the storage and the amount of time that will be required to for data communication. So in this particular technique, what do we do? It is also based on the frequency only. It is also based on the same technique. You can say that the frequency. There are certain characters which are high frequency, and there are certain characters which are low frequency. But they have considered the same information, but the methodology to create the code is different from what we did in the Huffman coding. So in this particular technique, we sort the list of symbols in the decreasing order of the probability. So you can see the probability or the probability or the frequency is same thing. So either you can have the probability of a particular alphabet in the given text, or you can have the frequency of the particular alphabet in the given text. So it is you can say. So in this particular technique, what is being done is we split the list into two parts. So with the total probability of both the parts being close as much as possible. So here you can see, first of all, we are going to sort this particular thing, and we are going to find out either the sum of the frequencies, or you can see the sum of the probabilities. So if we are able to find, let us say if we take the sum total of A and B, and we take the sum total of C, D, E and E. So what is the, if they are coming very close to each other, that means the difference is less. We are going to partition this particular table at that particular level. So you can say we can divide A, B and C, D, E in between if the difference, let us say it is sum of A and B is 50 and the sum of 30.35 and 0.45. So we can divide it between A, B and C, D, E into two parts. So after every division, what do we do? After every split, we assign the 0 to the left part and we assign 1 to the right part. So, and we keep on repeating it until all the symbols are split into individual groups. So you can see we are in the Huffman coding, we were following the bottom-up approach. We were considering them as the leaf node first, and we are moving from bottom to top, creating the root node. And here you can see we are applying the top-down approach, and we are moving from top to bottom and creating the individual leaves at the end. So these codes are considered accurate only if the code of each symbol is unique. So here you can see the same example. So what is being done? So the total is being taken. The data is sorted in the decreasing order of their probabilities, and on the basis of that, the split is being done. In this split, here you can see the appropriate split has been found at you can B. So the DB and is taken on the one as one child, and AC is taken as another child. So here you can see, so the left child is assigned the 0 value and the right child is being assigned as the 1. So in that case, then similarly, now we see in the left child, we know we have only two nodes. So you can say, all the two characters, we have to just split them. So the left will be assigned 0 and the right will be assigned the 1. So here in the right hand side, we have three characters. So we can take a sum total of, we can see that A is 0.22, and we come back. If we take A and C, if we try to split at C between C and A, so there will be unbalance between the two. So we are going to split A and C. So because the sum total of C and A is more or less closer to A. So what do? We are splitting that at the C. So we get A as a leaf node, and then we have and we are assigning 0 on the left hand side, and we are assigning 1 on the right hand side. And then we say we are left with C and E, and we just have to split these two characters. So when we are splitting now, since at every level we have zeros and ones, and now converting getting the code for this particular getting the codes for each character from this root, we know we have to read through the leaf node. So here you can see the code for D is 0 0, and the code for you can say B is 0 1. So here you can say, here we have both in the Huffman coding as well as in the Shannon Fano coding. In both the techniques, we are getting the variable length codes. It may mean that some characters are having a codes of a single digit, and some characters are having the codes of the 2 digit, 3 digit, 4 digit, like that. And this helps in this kind of you can see these variable length coding techniques. They help us in reducing the memory, because small number of digits means the small number of bits which are required for the storage. So therefore, if we have to find out the code, you can start from the bottom also. So here you can say what is the code for C? 1, then 1, and then 0. And the code for E is 1, 1, and 1. So we are moving from left to right and right to left. And so traversing each part of the tree, you can say, for every branch, because it is leading to one character. So every branch of the tree is representing the code for the leaf node, or because leaf node is having a particular character from the text. So this is how we use a Shannon Fano coding for creating the codes, or you can say for the data compression. Now, since we have been using this, so the question is how much memory we are able to save when we are using these techniques. So here you can see, if we have these symbols A, B, C, D, E, and we are using the Shannon Fano coding, let us say we are able to generate these codes. And then if you see in the occurrence in the 100 character length text, it takes this much of space. So here you can see the number of bits using the ASCII code for this, when we are using the 22. So here you can say, if we see the occurrence in number of bits which we require for storing the character symbol A, it requires 176 bits. But when we use the Shannon Fano coding, it requires 44 bits. Similarly, for B, C, D, E, we can calculate the number of bits which are required using the ASCII characters, which are used on the fixed length encoding scheme by the machines. And here you can see the number of bits which are required while using the Shannon Fano code. So here you can see the total length when we take the sum total of A plus B plus C plus D plus E, because that is the total memory requirement for all the characters. Using that Sky codes, it requires 800 bits, and if we see the Shannon Fano coding, it requires 220 bits only. So it is nearest multiple of 8, right? So the text needs only the 30 bytes, whereas using the Sky code, text needs 100 bytes. So you can see the difference. We are able to save the 70% of the memory, or you can almost, using the Shannon Fano coding. So this is the similar kind of you can say calculations you can check. So you just, because the character will be, requirement will be same, but for the Shannon Fano you can say that using the Huffman coding, you can see the encodings that we have used. On the basis of that, again you can calculate the number of bits which are required, and you'll be able to see. So whenever we are using the text compression technique of Huffman coding or Shannon Fano coding, we are able to save almost 40 to 50%, 50% of the memory for the text compression. So now you have to do this question and tell me the solutions for this. So this is the you can say these are the frequencies which are given to you for some text. Now you have to encode the given text using the Huffman coding as well as Shannon Fano coding, and then you have to calculate the number of bits which are required for storage using the Huffman as well as Shannon Fano coding. Start working on